Critical values come from the chart. This particular critical value, noted as t sub 0, comes from a sample size of 5, meaning 4 degrees of freedom, right-tailed, so we'd read the one-tailed line. Alpha is 0.10. On the big bell curve of life, 3 sigma limits on each side, 1.533 would be right here. That's my critical value from the tail, from the chart. It cuts off what's called the rejection region. That rejection region's percentage is considered to be alpha. The calculated value came from the sampling distribution formula. I've done the calculation for you and found my value to be 1.783. Notice it falls in the rejection region. If the calculated value falls in the rejection region, you should reject. I'm going to reject the null. Now I want to introduce the concept of a p-value. P stands for the percentage of the curve, or the probability, from the calculated value to the closest tail. So shaded here in red, that's my p-value. You can see that it takes up less area, or less of a percentage of the curve, than the black does. So I'm going to say p is less than alpha. In this example, n is 10, so 9 degrees of freedom. 1% is in the tail, in fact in the left tail, and according to my t-table chart, the value would be negative 2.821. Three sigma limits on each side, negative 2.821 would be around here. My calculated value from the sampling distribution formula I have done for you and found the calculated value to be 1.362. It's negative and it's on the left. I can see that the calculated value is not in the rejection region, so I'm going to fail to reject the null. The concept of the p-value is the percentage of the curve from the calculated value to the tail. If I color from the calculated value to the tail, it covers more area than alpha. So I list this as the p-value is greater than alpha. In this problem, n is 15, so there are 14 degrees of freedom. The percentage in the tail is 0.05. It's left-tailed. According to the t-table chart, my critical value will be negative because it's left-tailed, and the value is 1.708. On my bell curve, that would fall approximately here. Chart value, negative 1.708. If I shade to the closest tail, that's my alpha, 0.05. My calculated value from the sampling distribution has already been done for you, and it was calculated out at negative 1.051. It's not in the rejection region, so I fail to reject. If I look at the concept of the p-value, which is the calculated value to the tail, the percent that holds there, shaded in, would be more than black, more than alpha. So P is greater than alpha. One last time, the critical value from the chart at 26 in the sample, so 25 degrees of freedom, right-tailed 5%, would be 1.761. It cuts off approximately 5% of the curve. That's my alpha. If I do the calculated value from the sampling distribution, it falls at 1.987. and it does fall in the rejection region. If I want to compare the p-value, which is the calculated value to the tail, it shows up just a little bit less than alpha. So let's notice the contrast. In question 1, p was less than alpha, we rejected the null. Question 2, p was greater than alpha, we failed to reject the null. Notice the contrast. Question 3, p was greater than alpha, we failed to reject. And question 4, p was less than alpha, we rejected the null. Try to build the rule, which will say, if p is less than alpha, reject the null. This means your results are statistically significant and they can be inferred to the population. Part 2 of our rule, if p is greater than alpha, we need to fail to reject the null. The results are not significant. They are only in the sample. P-values are listed in most scholarly articles that are quantitative in nature. Here, p is less than 0.01. That means whatever the probability is, it's less than alpha. Alpha was 0.001. It's also statistically significant and can be inferred to the population. The second example shows the p-value is less than 0.09. So whatever the percentage of the curve from the calculated value to the tail is, it's less than 0.09, which would be alpha. If p is less than alpha, then the null hypothesis was rejected. Whatever the researchers were saying is correct, and it can be inferred to the population. The same holds true with p less than 0.05, statistically significant. P less than 0.01, statistically significant with an alpha of 0.01. P less than 0.005. Alpha was 0.05, but the p-value, the percentage of the curve from the calculated value to the tail, shows such a small amount, it's less than what they were willing to be wrong, and it's statistically significant. P is less than 0.001. The percentage of the curve from the calculated value to the tail is so small, it's less than what they were willing to be wrong. The percentage they were actually wrong was less than the percentage they were willing to be wrong, so that means they're right. What they were saying in the article is true and can be inferred to the population.